Hello, everybody. My name is Dan Painter. I am the Product Training and Development Manager at Flint & Walling, and I will be hosting today's web conference entitled 4-inch Submersible Pump Ends. Before we get started, just real quick, this particular broadcast is being recorded. So at some point, if you want to review it or share it, simply go to our website, www.flintandwalling.com. Click on the training tab, and when you do, a drop-down menu will appear. Click on webinars, very much the same way that you did to register for this event today. But also on that same page is an archive of recorded web conferences. And since I haven't done a conference on a 4-inch submersible Flint & Walling pump end recently, I'm going to go ahead and record this one so that it will be out there as well. Other than that, I'm going to be putting together another schedule of web conferences at this point, probably extending well into the summer. And I'm going to be coming up with some new topics and different subject matter and so on and so forth. So again, check on that website periodically, because as soon as we get those scheduled, we'll get them up and posted. We're actually doing some repeats of what we did early in the year, but in the current condition that we're all faced with, it's nice to be able to reach out and at least have some communication this way. This conference won't take, typically it's about 35, maybe 40 minutes long, but certainly not an hour. With that, we're going to go ahead and get started, and I'm just basically going to walk you down through a Flint & Walling submersible pump end. When we look at these pumps, and we're especially 4-inch submersibles, I just wanted to throw this up here real quick because there are a variety of these that we offer. On your left-hand side of your screen, you'll see our 4-inch subs that range from 5 to 27 gallon a minute. And the cast iron and stainless steel submersible pumps will go from 1/2 to 5 horse. The thermoplastic pump is going to go from 1/2 to 1 horse. But again, available in 5 to 27 gallon a minute, followed by our deep sets. We manufacture deep set pumps, 2 to 7.5 horsepower. Those also range from 5 to 27 gallons per minute. And the high caps, the 35, 55, and 85 gallon per minute series with a 2-inch discharge. So much of what we're talking about in the design today kind of crosses over to the pumps on your screen. With that, I'm just basically going to walk down through just the pump end. I'd like to identify the key or critical components, their functionality, as well as their material of construction. Primary purpose for this is to just refresh some of you on how these pumps are constructed and how they're designed on the inside, because in the day and age that we're in, most pumps, whether they're in warranty or out, are simply field scrapped and replaced. I get that. But at the same time, that field scrapping policy, which is industry-wide for the most part, if there is a disadvantage, it's over time we can become disconnected with how pumps are constructed, especially if any changes have been made. So with that, we're going to start off up here with the discharge, and a little generic conversation at this point, but most every pump manufacturer will have a couple of components up in this discharge. One is what we call a check valve, or a Poppet check valve assembly. So when we talk about the check valve, and let me just say this, I'm going to date myself in so doing, but back in the mid-70s, I sold several different brands of submersible well pumps. I worked for a supply house over in Ohio at the time, and I will tell you that not one of those brands back in those days ever had any check valve failures, not one. And the reason for that is that back in those days, if you bought a submersible pump, you didn't have a check valve in it. So somewhere along the line, some engineer got the idea that if they could build a check valve into the discharge of the pump, there was a potential to save the contractor time and money, because every water system has to have a check valve. But that all said, I'm going to share an opinion here in a minute or two. When I'm in classroom and I have a classroom of contractors, I throw this slide up on the projector screen, and it says, and I ask them, I go, look, I'm making a comment here that the average pump cycles, 20 times a day. And I look out over the group and I said, let me ask you a question. Do you think that number's too high, or do you think that number's too low? I have never had anybody tell me it's too high. Most of the time, they feel like that's a very conservative number, that there are pumps out there that cycle many, many more times than just 20 times a day. But that all said, let's take a conservative route here. If a pump does, in fact, cycle 20 times a day, then that means 7,300 times a year, we're going to have to expect for that check valve to not just open and close, but more importantly, open and seal. That's 7,300 times a year. So I'm going to share an opinion with you now. And I think it's shared by all pump OEMs. I think buried in their installation instruction manual somewhere, there will always be a recommendation for an additional external check valve to be put on the system somewhere. The fact that these check valves are in the location that they're at, that being the discharge of the pump, I'll share my opinion. I personally think, and this is just an opinion, but I think that that's probably one of the worst locations that a check valve could be subject to in a water system. And the reason for that, the reason I have that opinion, is if you were ever to see the water as it's exiting the discharge of the pump, not coming out the drop pipe, but out the discharge of that pump, that water is spinning at about the rate the motor turns, which is 3,450 RPM. So it's a very, very turbulent. I'm going to try to get my my highlighter up here. But in this area through here, that's a very, very turbulent environment. And like I said, the water's spinning like crazy. And so as a manufacturer, you're trying to get either a rubber O-ring or rubber gasket or whatever the design might be. And you're trying to make that Poppet check or that check valve stable in a very unstable environment is a bit of a challenge. So there's some things that Flint & Walling has done. We've spent a lot of time on check valves over the years, and there's some things that we've done that I believe have given us at least a stable component in a very, very unstable environment. So as you look at this check valve on your screen over here on the right, this is kind of a blown up view of what's in this pump discharge over here. The poppet is conical in shape. That's by design. Tapered. That's by design, so that as this poppet lifts up while that pump is up and running, and when the pump shuts off, we rely on that taper to be somewhat of a self-centering aspect of that check valve so that it can get back down, seat, and we get a good sealing surface across this O-ring and the sealing surfaces itself. The poppet stem is rectangular in shape, as you can see in your screen, and that stem moves up into this guide, which also has a rectangular opening. So the notion here is when you put a rectangular object in a rectangular opening, you can't spin it. And so we wanted to create an anti-spin feature, excuse me, to this check valve. Otherwise, if you don't have that feature built in, that check valve is going to sit there and twirl around and chuck and spin and prematurely wear the sealing gasket out or the rubber O-ring. We also cap the top of that guide. As you can see here, we cap it. And this is an enhancement we've made to this check valve over the years. The older style, if you look to the left-hand side where I have my cursor, the older style, when this poppet used to come up, that stem would actually come right up out the top of that guide, so it could pass right through that area. In fact, you can see just the tip of it barely sticking through on this illustration on the left-hand side. That doesn't happen anymore. We've totally cased that top off. And for this reason, we do a lot of destructive tests at Flint & Walling. One test that we have that we've conducted quite frequently when it came to these check valves is what we internally call the snow globe. Now, most of you know what I'm talking about. It's a little souvenir type of thing that kids really like a lot. You can pick this little thing up, shake it, and you see all the little glittery things slowly settle back down to the bottom. At least I've always referred to them as snow globes. We created a test at Flint and Walling that kind of mimicked that. We hit the water with a lot of sand, a lot of fine sand, a lot of different coarse sand. And what we wanted to make sure is that when that pump shuts off and there is sand in that drop pipe going up to the top of the well or up to the pitless, as that pump is sitting idle, that sand will have a tendency to settle back down within that drop pipe. And we did not want to get any of those kernels of sand that could possibly drop in between the poppet stem and the guide and lodge in there that might cause that check valve to either lodge or stick open or stick closed. And so, again, with that cap on the top, we don't have that problem anymore. So any sand-bearing water supply that you might run into, and especially I've had some contractors refer to certain types of sand as sugar sand, and they call it that because it is so fine in its nature. I believe I've got a video coming up here. These are real fast videos. Whoops, I got feedback. Okay, I'll turn the audio portion off. But just to give you an idea of how this poppet reacts in a submersible well pump, we had some lab technicians that drilled a hole in the side of a discharge, put a sight glass in there so that we could actually film that poppet as the pump was up and running. And again, these are very short clips. They're not but maybe 3-4 seconds long. But this is a 19-gallon-a-minute pump, 3/4 horsepower. We're going to run that pump at full open discharge. And the lab techs also took a permanent marker and drew a straight line right down that conical portion of that poppet so that we could look in there and see what happens when this pump is up and running. And so here you go. We're going to go ahead and fire this video up. You're not getting any of the audio, but as you can see, that line it wasn't chucking back and forth. It wasn't trying to spin. So we feel pretty confident that we were able to create an environment for this poppet check valve that's got stability. Over here on the right-hand side is the same test that we did. We ran this on a 27-gallon-a-minute pump. Not quite as easy to see, but you can see the red line. I got my cursor on it right there. And again, this pump's going to pump at full open discharge at 27 gallons a minute, and you'll notice that line isn't moving right, it isn't moving left. And that happened to be let's see, I think, well, this one over here was a 3/4 horse, 19 gallons a minute, and I'm not sure whether this was a 1 or 1.5 horsepower, 27 gallons a minute. But that video, those two short videos, can kind of illustrate what I was talking about when mentioning that this check valve is stable. I got to move my dashboard out of the way because I've got some things coming up on my screen that I can't see. So just bear with me for a second here. Oh, okay. All right. So what I got up there is that, you know, these are just some multiple designs that are out there. I can't answer for most of them, but the one here that is representative of a Flint and Walling, I was able to show you how that poppet was pretty stable in that environment there. So with a check valve, you know, you want to make sure it opens and seals. You want to make sure that it's able to properly react in a turbulent environment. What is the expected life cycle? Well, we've cycled our poppet check valve 1 million times. So that's like the life of 10 pumps. But anyway, that was our protocol for cycling that check valve. That check valve is removable as well. I should have said this when I was on the previous slide, but this guide has, as you might have noticed, kind of looked like a wagon wheel. So you can go down in there and catch those ribs, and you can turn that check valve right out of that discharge. So it is a removable check valve as well. There's a better picture of it. Just below the check valve is another critical component, and it's called a discharge bearing. And that's right here. And let me go back to this slide. That's this discharge bearing right here. Over on this right-hand side, you can see how that bearing encases the pump shaft as it comes up. This is the only bearing in the pump end itself. So we want to make sure we do a good job with that component. The only other bearing you got is down in the bottom of the motor. So when we look at the discharge bearing, we use, on our pump ends, we use what's called a closed, no lead, bronze discharge bearing. Keyword, it's closed at the top. If you're not using a closed bearing, then you're probably going to be using some type of a sleeve bearing, as you can see illustrated here. Now, our design team at Flint & Walling doesn't believe that a sleeve bearing on a shaft like this is watertight. We believe that water can, and in fact will, get between the bearing and the shaft and have some ability for it to flow through that area. Not a lot, but it doesn't take much. If you happen to have a sand-bearing water supply, and if it happens to be this so-called sugar sand that is coined because of the fact it is so fine in nature, then would it not also be possible, that's what we ask ourselves, where some of that fine sand could also pass between this bearing and this shaft? And if that does in fact occur, could it possibly prematurely wear out a discharge bearing? We believe the answer to that to be yes, it could happen. And so that's why we opted to go with this closed bearing at the top, because water can't pass through that area. It's closed. And if water can't go through there, then logic would say that we're not blowing sand through there as well, because there's no path for it to travel. In fact, this closed discharge bearing is what led us to the design on that check valve I talked about earlier, and going ahead and capping the top of that off as well, just to keep water flow and debris from going through a critical portion of this pump end. So that's the discharge bearing. And when we look at discharge bearings, there's varieties of them used in a variety of different submersible pumps. Some are made out of ceramic, some are made out of plastic, some are made out of rubber. Kind of these two bearings here are like sleeve bearings. This one is, in fact, it is a closed bearing, but it's made out of a plastic material. And again, the reason we opted to go with the no lead bronze closed bearing was because if you get into situations, sometimes they're outside of our control, where a pump is potentially or possibly deadheading, is pumping against a closed valve, which is, in my opinion, it's one of the most destructive things you could ever do to a pump. Or if it's running dry, no water going through it, both of these conditions will generate a considerable amount of heat rise. So if you're deadheading, you're churning the water over and over and over, the same water over and over and over again, it would rapidly heat up, and you get a pretty significant heat rise, as you do if you're running dry. And so in some destructive tests that we do, we can see that if the components are not designed for heat, then obviously they're not going to withstand it. So for instance, this here melted down in approximately 48 minutes. The rubber bearing over here also melted down under an hour. I think it might have hit 54 minutes. And the ceramic, I don't have an image of that, but the ceramic is a great material. I used to be in water treatment years ago, and I used a lot of ceramic in water treatment. It's a very smooth surface. It's a great sealing surface. It's very hard. The problem is it doesn't like heat and temperature change. When you get rapid temperature changes, you go from hot to cold, cold to hot. What will happen with ceramic is it will fracture. It'll create a hairline crack down the side of the bearing, and at that point, that bearing is of no use anymore. This is a picture of a Flint & Walling discharge with the bearing in place. That was after 4 hours of run dry. People said, well, how you run a pump dry for 4 hours and not run the motor? I can answer that. We put that motor down in a tall bucket of water, and there was a hole drilled in the bottom of it. We fed water into the top of it, so water essentially was moving past that motor the entire time we're running this test. But from the suction screen up, that was all above the water level, so it in fact was running dry. But there's where that bearing can show its benefit, is in conditions that sometimes we don't have control over. And again, you know, I challenge contractors that if they don't know, find out, you know, what particular brand they may be selling. It doesn't matter, but how do they react to sand and abrasives? A bearing is designed to support that shaft. That's its sole objective. But we do know that it's going to be subject to conditions such as this, sand and abrasives, and we want to know how they react to that. And how do they react to excessive heat rise? Moving down from the discharge now into what some people refer to as the stack. It's basically in a submersible pump. What we're doing is we're placing impellers one on top of the other. Far right image on your screen actually shows a real flint walling stack. This is what it looks like. We use these plastics are all different. We use dissimilar plastics in the makeup of our stack. Because, again, with heat rise, if you've got everything made out of the same plastic, then you get a meltdown, one on top of the other. Everything just fuses together and becomes one giant mess. Inside that stack are these components that are showing up on your screen now. Every impeller is going to have a thrust washer placed on the hub. And then in the case of a flint walling, that impeller is going to sit down into a diffuser and then be secured in that diffuser with a diffuser plate. So that entire assembly with the diffuser, the impeller, thrust bearing is referred to as a stage. That's what we would consider a stage. And I want to talk about some of these components now as well. I want to look at that thrust bearing. Now, flint walling uses a stainless steel thrust washer here. We actually stamped those out in Kendallville, and it wouldn't be a gold color like this. It'd be more of a silvery, shiny color, but nonetheless, it's made out of stainless steel, and we put that on every single impeller or every single stage. And the purpose of a thrust washer is to compensate for what's referred to as upthrust conditions. Well, to define what an upthrust condition is, pretty easy. It's a sudden and forceful upward movement. So the motor that are on the end of these pump ends, these submersible pump motors, these rated at 3,450 RPMs, they get to that speed in about 0.4 of a second. So that's pretty sudden. And with the submersible pump always wanting to pump upwards, that's where we can end up with an upthrust condition. And so when you get upthrust, you got water coming in through the suction screen, and it flows upwards through that stack. All those impellers, all those diffusers that are in there, they want to just move right out the top of the discharge, right along with the water. That's what's called an upthrust condition. It's not a desirable condition to stay in, but every pump's going to see upthrust at some point in time, such as the very first time you place a pump in a well. You will be, not maybe, you will be in an upthrust condition. Why? Because in the drop pipe, the water that's in the drop pipe is at the static level, and everything above that is void of any water. So you've got a drop pipe running up to the pressure tank, and it's mostly empty. You got a pressure tank, doesn't have any water in it. And so when you fire that pump up for the very first time, it's got no head pressure against it. There's no load against that pump that helps keep those impellers in that stack where it's supposed to be. And so everything wants to ride up until that water line becomes full, and you put water in that tank and it starts to see back pressure or head pressure from that tank. You'll be in that upthrust condition for that time that it takes to get there. You can also you'll also be in an upthrust condition anytime you're pumping a pump open discharge. And, you know, I know a lot of contractors will use a pump when they develop their wells. There's a variety of ways that I've seen across the country that drillers use to develop wells. Some use air, some actually drop a pump down in the well and pump all that garbage right out open discharge. And I've seen those pumps pump for a couple of hours in order for that water to eventually clear up. Well, that whole time that pump is pumping open discharge, it will be in upthrust. And so you want a good solid washer up there to compensate for that condition. If a pump's not sized properly, and that's not typically the case so much with these fractionals and these, these 5, 7, 10 gallon minute residential pumps. But when we get into like deep set pumps, and you saw that on the one of the first slides I showed, you get a deep set pump that's designed to go down several hundred feet in a well. If it's not sized properly, that pump can be an upthrust. And in fact, I'm pretty certain there are Flint Walling pumps out there that, for one reason or another, didn't get sized properly, and they're going to be an upthrust their entire life, the entire time that they are in the well. And then, my opinion, and this is just an opinion, I believe a pump goes into upthrust every single time it powers up, only for a fleeting fraction of a second. But again, you take that 3450 RPM motor that comes up to speed so fast, I think you get that sudden jump just for a second inside that stack. A lot of people say, well, that's no big deal. No, it's not a big deal. It does it 7,300 times a year, though, remember? And you told me that number was low. So over time, you don't want to wear these thrust bearings out, which is why we use stainless steel. But not everybody does. And so, again, that thrust bearing or that thrust washer serves a purpose to compensate so that you're not getting light plastics to rub together. And eventually what will happen is they can actually spin weld themselves together if they get that much going on. Moving to the impellers. These are some different designs of impellers that we can find in submersible pumps. And Flint Walling impeller is this black one on the top left. One thing I'll point out with this impeller while I've got this image up here on the screen, if you ever were to look at a Flint Walling impeller closely, what you will notice is that this top segment of the impeller right here that I'm running my cursor around is slightly smaller in diameter than the lower segment. And if you look closely, you can see where those veins are coming out between the two segments. And the veins come all the way out to the very far outer edge. That's where we get our efficiency. But some contractors call a Flint & Walling a loose stack. The tolerances are not tight, and that's by design. In fact, we manufacture what we call a floating stack, so that when that impeller sits down in that diffuser, like you saw on the previous slide, and this pump is under a load, up and running, that design of that stack is such that that impeller should float within that stack. It shouldn't be rubbing top, and it shouldn't be rubbing at the bottom. We get a lot of life out of a Flint & Walling pump, and a lot of guys know that, but they sometimes don't really know why that is. And this is just one of the many reasons, is that the impeller design is such that it doesn't have excessive rub top or bottom. Rather, it will float within that diffuser. So, you look at the impeller down here, for example. I don't know whose this is. It doesn't matter. But pretty tight tolerance, and top segment, bottom segment, exactly alike. Let me show you what happens with sand. So coming up on your screen now are some images. Again, we run a lot of destructive tests at Flint & Walling, not just on our own product, but also much of our competitors will go through our audit tanks and our destructive tests because we like to be able to compare wear patterns. And that kind of gives us a grade card. So, for instance, this impeller that I was talking to you about just a little bit ago, if you look over here on the right, you can see what damage that sand has already done with this impeller. The tolerances are too tight, and so it'll eventually erode material away. Same with this second impeller, this more open design here. You'll look and you'll see the grooves going around there where that sand has cut grooves in and around that impeller. Actually, it distorted, looks like it distorted the eye of that impeller. But in the exact same test, for the exact same duration, the exact same amount of sand, everything being equal, this is what we suffered. We suffered a little bit of rub, just a little bit right there on the around the eye of that impeller. You can see it on that screen there. But that impeller, that little rub didn't do anything to that impeller, didn't change the integrity of it. In fact, our post-test performance curve looked almost like an overlay of the pre-test. So we fared pretty well in sand testing by that design. Diffusers, these diffusers that you see here, basically their sole purpose is to convert the velocity generated by the impeller to convert that into pressure. And again, as I mentioned previously, we want to make sure that we don't make all these components out of exactly the same material. If you do, this is what you can expect to happen. And this is an example. This is an example of the of a pump that everything in that pump, impellers, diffusers, everything was all made out of the same kind of plastic, and that's the kind of meltdown that you will get. Like I mentioned earlier, it just kind of melts right down on top of each other. So when we look at the staging again, I want to bring this up that what's on your screen now that's a half 10 gallon a minute pump in. That's what that is. And there are 8 stages. 1, 2, 3, 4, 5, 6, 7, 8. 8 stages in that pump. We don't keep staging a secret. It's in our brochures. It's in our price sheets. So when you order a certain model, horsepower and gallon per minute pump, we'll come right out and tell you how many stages are in there. I would challenge you to look at competitors' models of the same horsepower and flow rate, because what I find is that typically much of our competition is running 1 or 2 stages less. There has been some destaging take place in our industry over the last 25 years, just due to all the mergers, acquisitions, blah, 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 moving offshore for manufacturing. Knowing that pumps aren't repaired often, many pumps today are actually non-repairable, right? You can't even take them apart anymore. I don't see anything wrong with that. If people aren't repairing them, why make them repairable? But at the same time, changes then now can be made without a lot of people's knowledge. And so there has been some destaging going on. So I'd always encourage you to compare the staging of an F&W pump in, and I don't care what horsepower or flow, a gallon per minute rating, but compare that staging with maybe a competitor brand. And I think you're going to find that to be true, that F&W is typically going to have 1 or 2 more additional stages in a light pump in than much of our competitors would have. And that staging is has a direct correlation to performance, to increased pressure, and to the total amount of feet ahead that pump can withstand. That staging does. So if we look at a pump curve like you see here now, this pump curve on the screen now, I can tell you that's a pump curve for our 7 gallon per minute series, because all these sweet spots that you see along here are right at that 7 gallons per minute. But it wouldn't matter if we had 10, 15, 19, 27, it wouldn't matter. Our Flint Walling has always had a fairly steep curve when it comes to their 4-inch submersible pump ends. Now, that said, if you ever find yourself having to go left of that sweet spot, you have to move left on this performance curve. We underestimated the total dynamic head, perhaps, short changes on how far we were setting the pump. If we ever find ourselves operating over on this left-hand side, that's where those additional stages are going to really shine and show their face, because like I mentioned, there are competitive pumps out there with fewer stages, and they're designed to hit those sweet spots. As you might see now, they're designed to hit the sweet spots, but don't ask much more than that, because they start to flatten out really, really quick over there on that left-hand side. And so, again, that additional stage or 2 is what makes up for this difference you have in performance on the left-hand side of that curve. So that all, I guess I'm at the end of this. I feel like I went through it quick, but I look at the clock, we're at 2:35. I didn't think this would take much more than maybe 35 or 40 minutes. Again, I'm going to be conducting further web conferences probably at least through June, and I'll be scheduling those in the next week or so. I'm going to be throwing a variety of topics up there, ranging from city water pressure boosters to variable frequency drives. We can talk about ohming out motors. So I'm going to kind of shuffle the topics around, and I'm going to start recording these things. This one here, I got a message halfway through that said your recording stopped, so I have no idea what that's going to sound like. But anyway, I encourage you to visit our website, click on that training tab, and you'll see that schedule of web conferences that we're going to put back up there here very shortly. So with that, everybody, stay safe. Hope you picked up a little bit on how a Flint and Walling pump is constructed and maybe why we do certain things the way we do it. But our ultimate goal is quality and longevity, and I think that's a reputation that we have, and we need to live up to it all the time. We're only as good as what we do today. So look forward to speaking to you soon in the future. Until then, please stay safe and take care. Thank you. This web conference is now ended.